This is the second lecture about Chapter 6, the Laplace Transform. And in this lecture, I'll quickly review what we learned from the last lecture and also give a big focus to section 6.2, which really starts to get into the purpose for the Laplace Transform, more so than section 6.1 did. So let's quickly review what we learned about the Laplace Transform. The Laplace Transform is a transform or an operator that happens to be linear. It takes functions as inputs and gives you functions as outputs. The linearity can be expressed in a typical kind of linearity formula, the Laplace transform of a linear combination, like this. A times f of t plus b times g of t is the corresponding linear combination of the Laplace transforms of those individual functions, f and g. A times the Laplace transform of f plus b times the Laplace transform of g. It's a linear operator, a linear transformation in that sense. Some alternate notation that's commonly used is, you'll recall that the Laplace transform of a function of t we think of as being a function of s, a new variable, and so we might call this capital F of s, where capital F of s is the Laplace transform of little f of t, and maybe call this capital G of s. Some alternate notation. A very important property that we ended up using in section 6.1 is the fact that the Laplace transform of a derivative, which I'll write with Leibniz notation, where y here is a function of t, the Laplace transform of dy dt is s times the Laplace transform of the function y again being a function of t, minus the function value at 0. This is the fundamental property that essentially allows us to replace the differential equation with an algebra equation and then do the algebra and ultimately use the inverse Laplace transform, which is also a linear operator, though you really have to sort of build up a table of linear operators in a sense, just like in Calculus 2 you build up tables and techniques for anti-differentiation. It's a very similar kind of thing. I didn't say what the Laplace transform was. I didn't remind you of that yet. I'll do that now. The Laplace transform of a function little f of t is defined by using an improper integral. Improper integral from 0 to infinity of little f of t times e to the negative st dt. The t ultimately integrates out, leaving you with something that depends on s. You do have to think about whether this converges or not, and so sometimes there are conditions on s that help you decide whether it converges or not, though that doesn't really play such a big role as far as solving the differential equation goes. What are we going to do today here? Well, we want to justify the Laplace transform a little bit more with problems from section 6.1. The Laplace transform is more work than it's worth. Methods from chapter 1, like integrating factors and even the method of undetermined coefficients, are quicker than using the Laplace transform, less confusing even. And so you might scratch your head and wonder, why do the Laplace transform at all? Well, as we go on in chapter 6, starting in section 6.2, it starts to really prove its worth. What we apply it to, which we cannot apply the methods from chapter 1 to, are equations, for example, where the right-hand side, forcing function, if you will, is even discontinuous or non-differentiable. What would be an example? Well, I suppose we could put an absolute value function on the right-hand side, or some modification of an absolute value function. I'm going to do something different. I'm going to pick what's called a Heaviside function, kind of a funny name. I'm going to label it U sub 4 of t. In the textbook, this is called a Heaviside function after somebody named Heaviside, somebody with the unfortunate name of Heaviside. And what is it? Well, it's also sometimes called a UnitStep function. Its graph looks like this. It's equal to 0 for all values of t less than or equal to the subscript. Actually, strictly less than the subscript. So the subscript is 4, so I'm going to put a 4 on this axis here. That function is equal to 0 for all values of t less than 4. And when t is 4 or greater, the function value jumps up to 1. You've got something called a jump discontinuity for that function at t equals 1. It's actually a pretty simple function then in that sense. It's not a complicated function, though it doesn't really have a formula in the traditional sense. It is a useful function, especially for electrical engineering problems you'll see as you read section 6.2, where voltages can be switched on or off at certain instances in time. Can't say the word instances. There we go, I guess I said it. This function ends up being useful for those situations. It's a forcing function then for this situation where it's 0 forcing until time equals 4, and then it's a constant force of 1. We can't solve this using the methods of chapter 1. The Laplace transform really is necessary, and it does allow us to solve it. Let's try using the Laplace transform. So I take the Laplace transform of both sides. I'll write y prime to save time here. Use the fundamental fact that the Laplace transform is linear, so this becomes L of y prime plus 9L of y. And then use the other fundamental property that the Laplace transform of y prime is s times L of y minus y of 0, which reminds me that I really need an initial value problem. So I'll go back up to the top here and write an initial value. For example, y of 0 equals 7. If that's my initial value problem, now that I can replace y of 0 with 7. And this looks a little complicated, the way I did this here, algebraically, but there's two expressions involving the Laplace transform of y, this one and this one. Everything else is a constant. Well, I guess I have an s there. I can factor out the Laplace transform of this term here and this term here to leave me with s plus 9 times the Laplace transform of y. And the 7, I'm really subtracting 7 here, so I can add 7 to both sides of the equation and see that this equals 7 plus the Laplace transform of this Heaviside function that has a jump discontinuity at t equals 4. And now divide both sides by s plus 9 to say that the Laplace transform of y equals 7 over s plus 9 plus the Laplace transform of u4 of t over s plus 9. And then I would take the inverse Laplace transform of both sides and get the answer. Well, before we do that, we better figure out what the Laplace transform of this Heaviside function is. Let's figure that out now. It's not as hard as it might seem at first glance. Go back to the definition of Laplace transform as an improper integral and try to do the integral. u4, remember, even though it's a weird notation, it is a simple function. It's equal to 0 for all t less than 4 and equal to 1 when t is greater than or equal to 4. Think for a few seconds about that. That means the improper integral is not going to be that complicated. Think about what's going to happen. Think about how you might simplify an expression like this. Thought about it? When t is less than 4, again, u4 is 0, and you're integrating 0. And when t is greater than or equal to 4, you're integrating 1 times e to the negative st. Which ultimately means you can really replace this integral by an integral from 4 to infinity of 1 times e to the negative st. Like that. And that's not going to be so hard to do. It is an improper integral, so technically speaking it's a limit. And you should always remember that. Carry the limit sign along and only apply the limit at the end. Antiderivative of e to the negative st with respect to t. It's going to be negative 1 over s e to the negative st. T goes from 4 up to b. Plug in t equals b, you'll get negative 1 over s e to the negative sb. Minus what you get when you plug in t equals 4, minus negative 1 over s e to the negative 4s. If s is greater than 0, this thing is going to go to 0 as b goes to infinity. If s is greater than 0, which is what we would assume now. And the two minus signs will make a plus sign, and in the end you'll get an answer of e to the negative 4s divided by s. Technically speaking, for s greater than 0. Though again, that technicality is not a big deal. It's not relevant really for solving the differential equation. In general, the Laplace transform of u sub a of t can be shown to be e to the negative as over s, where a is any number, and ua of t is a function which is 0 when t is less than a, and jumps up to 1 when t is greater than or equal to a. So that's going to be useful now for the differential equation. Here was the previous slide. Going back here, I can replace this thing with e to the negative 4s over s. Doing so, and then taking the inverse Laplace transform of both sides, allows me to write y as the inverse Laplace transform of 7 over s plus 9 plus the inverse Laplace transform, after I make the substitution, of e to the negative 4s over, what was it? S times s plus 9. This one's not hard to do. I can pull out the 7, and then I need to recall what the inverse Laplace transform of 1 over s plus 9 is. That's based on the preceding video. We need to recall that the Laplace transform of e to the at was 1 over s minus a. And so the inverse Laplace transform of 1 over s minus a is e to the at. And what I've got here is 1 over s plus 9. The a is negative 9. So this becomes a 7e to the negative 9t. which isn't so surprising when you look back at the original equation. Up there, and think about the associated homogeneous equation with 0 on the right side. You'd have equivalently dy dt equals negative 9y, whose solution you could guess, and would involve an e to the negative 9t, a constant times e to the negative 9t. This does it. That's really yh, once you've plugged in the initial condition. But what about this thing? Well, if the e to the negative 4s weren't up there, it wouldn't be so bad. We'd use partial fractions if it were just a constant on top. I'm going to go ahead and use partial fractions anyway. Ignoring the e to the negative 4s, just focus on this part of the fraction. I'm looking for values of a and b that make that true. Equivalently, if I multiply both sides by s times s plus 9, make this true. And, oops, mistake here. That's just an s. If I plug in s equals 0, I'll get the equation 9a equals 1, so a is 1/9. And if I plug in the value s equals negative 9, this part will be 0, and I'll get negative 9b equals 1, so b equals negative 1/9. Okay, that doesn't immediately help me because of this e to the negative 4s up there. But it will be about to help me when I derive a fact, another important fact in this section. What is the Laplace transform of u sub a of t times f of t minus a, where f here is an arbitrary function? What we'll see when we do this derivation is there's a nice relationship between the Laplace transform of this function and the Laplace transform of f that will allow us to go back to the original inverse Laplace transform on this slide and figure it out. I'll go through this quickly. It's an improper integral. U sub a of t times f of t minus a, e to the negative st dt. Just like before, the u sub a will be 0 if t is less than a, and 1 if t is greater than or equal to a. So I can replace this by an integral from a to infinity of f of t minus a times e to the negative st dt. Now, I can't actually do that integral because I don't know what f is. But through a substitution, I can relate it to another important integral by substituting u equals t minus a, so that t equals u plus a and du equals dt. I can say that this improper integral equals the following improper integral. The t minus a inside the argument of f becomes a u. The t up there becomes a u plus a. And the dt becomes a du. And the limits of integration have to be thought about also. The lower limit is t equals a up here. Looking at this equation, that means when t is a, u is 0. So the lower limit of integration becomes 0. The infinity becomes infinity, in a sense, because infinity minus a is still infinity, though you really shouldn't think of it literally that way. But you can prove that the infinity is going to stay as an infinity. And watch what happens if I use a property of exponents that allows me to write this thing like that, and then factor out of the integral that part because it doesn't depend on u. something interesting happens when you think about it. I'm left with this e to the negative as in front and this integral right here. But look at that integral. That looks just like the integral for the Laplace transform of f of t, except it's a u in there instead of a t. But, you know, variables of integration are just dummy variables anyway. It doesn't matter what you call them. This thing in the box is still the Laplace transform of f of t. So I get e to the negative as times the Laplace transform of little f of t. Now you might wonder now, how is that helpful? I just derived that the Laplace transform of u sub a of t, the Heaviside function with jump discontinuity at t equals a, times little f of t minus a, which is taking the graph of f of t and shifting it to the right by a units if a is positive, is equal to e to the negative as times the Laplace transform of f of t. That's useful because if you go back up here to the top, this e to the negative 4s is like the e to the negative as in front of that preceding identity. And the 1 over s times s plus 9 is like the Laplace transform of f of t down here. Since this is true, since what's by my left finger is equal to what's by my right finger, can you get those both in? Yep. Since those are equal, if I take the inverse Laplace transform of both sides, I'll get equal things too, meaning that the inverse Laplace transform of what's by my right finger down here in the lower right is equal to what's by my left finger without the L in front of it. In other words, for our example, taking into account the partial fractions, I'll just put the 1/9 out in front. 1/9 e to the negative, we want to take the inverse Laplace transform of e to the negative 4s over s, and then subtract 1/9 times the inverse Laplace transform of e to the negative 4s over s plus 9. If you wrote it down, compare it with what you see here. Again, the a is 4. And in this case, the L of f of t is 1 over s. We know the Laplace transform of the function 1 is 1 over s. Therefore, this thing becomes u sub 4 of t times 1 shifted over to the right by 4 units, because we have the f of t minus a in there, but the constant function 1 shifted to the right by 4 units is still the constant function 1. And this thing becomes u sub 4 of t times e to the negative 9 t minus 4. The negative 9 comes from the fact that we have a plus 9 down here. And the t minus 4 comes from the fact that we have a negative 4 up there. Let's just jump to the answer here. So y, using what we found earlier, is 7 e to the negative 9t plus the difference of these two things, and I can factor out a 1/9 u4 of t times 1 minus e to the negative 9 t minus 4. Now, if you weren't paying attention real well, I'm sure that went by too fast for you to really digest. Okay, and so you're going to have to perhaps re-watch that and read the book and really try to get it right. But let's see if we can use Mathematica to at least confirm its correctness. The Heaviside function with jump discontinuity at t equals 0 can be plugged into Mathematica in a couple different ways. You can either use UnitStep of t, where t goes from, let's just graph this over -3 to 3. UnitStep will do it. So you see how that has a jump discontinuity there at t equals 0. And if we want to shift it over to some other value of a, like a equals 2, we just need to translate this graph to the right by 2 units in that case. So here's the graph that has the jump discontinuity at a equals 2. So that would be u sub 2 of t in the book's notation. And another way to get Mathematica to graph this, another name for it essentially, is HeavisideTheta. I'm not sure where the theta comes from, to tell you the truth. Though one funny thing happens here is that it actually draws a vertical line there at t equals 0, whereas it doesn't when you use the unit step, no vertical line. So I guess using unit step is perhaps better. But either way should get you the right thing. Although I think with what I'm about to do, Mathematica spits back Heaviside of t, HeavisideTheta. What I'm going to do is I'm going to check that the inverse Laplace transform of those things that I had on the screen are what I said they were. For example, e to the negative 4s over s. When you use inverse Laplace transform, the variable of the function you are taking the inverse Laplace transform of is s, and so you need an s next. And you want the answer to be in terms of t, so you put a t next. And there you go. HeavisideTheta, well, something funny here. HeavisideTheta of n plus 4. Just think of that n as a t. I don't know why it's an n. I'm a little confused about that. Haven't looked into it. You should think of that as HeavisideTheta of t plus 4. In other words, u sub 4 of t. HeavisideTheta of t minus 4. Did I say plus 4? HeavisideTheta of t minus 4. U sub 4 of t. And the other one, I had an s plus 9 in the denominator. And look over here, we have the u sub 4 of t right there. And here we have e to the negative 9, t minus 4, really, if you imagine that the n is a t. So it really is, we didn't really do that correctly, and you should take the time to make sure you go back and study that. I know it went by quickly because time is getting short here, but take the time to do that. Maybe I should state the general property. Let's see. I guess I did that already. What I want to end this video with is showing you some examples of some other discontinuous functions that you'll encounter, especially if you're in physics or engineering. The most important discontinuous, actually non-differentiable function is the absolute value function, and hopefully you're all familiar with its graph. If you wanted to make that look more like the true graph when the scales are the same, let's see, aspect ratio set to 1 will make that look more like it should when those scales are the same. Look like a true V like that. So that's the most important non-differentiable function to know. It's interesting, and I'm just going to go quickly through these, to show you that you can make lots of new non-differentiable or non-continuous functions by combining these different functions that are like this. For example, this one is absolute value of t plus absolute value of t minus 1. Produces an interesting graph. If you ever wanted to make a non-differentiable function that looked something similar to that, making a modification of this function would do it. If you put a subtraction sign in there instead of an addition sign, you can get a function that looks like this. Still continuous, but not differentiable there or there. Here's UnitStep, which is again our Heaviside function with the jump at t equals 0. If you subtract UnitStep functions, maybe where one of them is shifted, so this would be u sub 1 right here, you can get interesting graphs, like that one. That's u sub 0 of t minus u sub 1 of t, really. If you put a 1 minus t in here instead of a t minus 1, right there, that's kind of interesting. You get a function with 2 steps. There's a function called the floor function, also called the greatest integer function, sometimes int function on calculators, int. It's got a bunch of stairs that actually go on forever and ever. That's the floor function. Here are some interesting related functions. T plus the floor function looks like that. Makes those steps slanted. T minus the floor function gives you a sawtooth wave, something you might see in an electronics class. T minus the floor function plus the floor function of negative t gives you downward sloping steps with upward tilts. Subtract the floor function from t squared. You can do something like that. That's pretty wild. And some other interesting things you can do if you combine arcsine with cosine, or vice versa, arccosine with sine, you can get this kind of sawtooth wave. That's called the triangular wave. And the function sine of t is interesting. It's got a jump like this, and actually this is inaccurate. It doesn't have a vertical line there. It actually has a value of 0 when t is 0. If you combine this with a sine function, you can get a square wave. Sine, SIGN, has a value of +1 if the input is positive, has a value of -1 if the input is negative, and has a value of 0 when the input is equal to 0. So I'm combining sine with sine, and that's the end of this video. Similar, though,